For the sake of time, I'm going to do this section very briefly, but there's a few slides in here in the geologic setting that I think are pretty essential. Number one is where it's located, just because it's so far away. So the what I'm going to be talking about today is the Anticoya porphyry copper deposit. It's located within the early Cretaceous porphyry belt in the coastal Cordillera of northern Chile. I'm very specific about that because there's about four. There's a bunch of different belts in the Chilean Andes where you have large porphyries. So it's not to say that Anticoya is like amongst the largest. That's Escondida and El Teniente and others. But this porphyry belt in general is very poorly studied, and Anticoya is within that belt amongst the largest. And it's interesting too because of the age. It's quite old and compared to how young most of the Chilean deposits are. So yeah, so just to situate everybody, it's located up here. Over here is the capital of Chile. This is Santiago. And then when you zoom in a little bit, it's in the Antofagasta region, but it's actually closer to this city over here, which is a big mining hub. Got a bunch of people coming back in. The other thing I wanted to point out here before we got started is that it's not to say that there's no hypogene mineralization here, but what they are mining is the oxide and the mixed zone. In terms of mineralization, it's about 350 meters thick. It's composed of a bunch of these minerals, which are all types of supergene copper minerals, including sulfites, carbonates, some silicates, some limonites, and I think I forgot to say oxides. There's some sulfide, but not as common, and it's in this supergene enrichment blanket. In the hypogene, there is mineralization, but it's not, again, what is being mined. Okay, the other thing important here to understand is some of the mining process. So it's an open pit mine, and it's leaching the oxide or using this copal core technology. It's a two-stage hydrometallurgical process that first extracts and then upgrades copper ions from low-grade leach solutions into a solvent containing a chemical that will selectively react with and bind the copper in the solvent. That is what I want to say over there. And then the problem statement. So the majority of the mining at Anticoya, as we said, is within the oxide resource. That's about 30% of the ore coming from the sulfate resource. And the sulfate is very important. The resource is comprised of very complicated mineralogy that affects the plant performance as well as the leaching. So the idea here was to generate an unsupervised 3D model to a mineral domain model to test work selection, and then to create a machine learning model that predicts acid consumption domains to save the mine both time and money on future programs that look at expanding the geomet block model. So by using hyperspectral image data, we wanted to both map the required minerals that we needed. So these sulfates, these oxides, these different silicates, these carbonates. And then the idea of using this is also to continuously update the model in near real time as long as you have core being scanned. Okay. So now let's have a look at the spectral data, which is very cool and exciting. So the system that we used in this study was called a core scan HCI 4.1. This is the spectral range of the veneer and of the swirl. So basically 450 to 2500 nanometers, which was the range that we needed. There's about 240,000 spectra per meter. The spatial resolution, 2500 micron. The spatial sampling, 500 micron. and the spectral resolution is 2 nanometers. Above is the 3D model built with only problematic mineralogy. So first, just looking, there's no trends in here, but first just looking at just where are the carbonates, where are the clays, where are the iron oxides, where are the sulfates. And at left, what we're going to do later in the next section is we're going to look at statistical domain modeling, which is probably a better solution than to just doing this basic style of mapping. Okay, so this is the mineral library. It's in Spanish, but the names are fairly similar. So basically, most importantly, what you can see is that it's a complex mixture of carbonates, oxides, sulfates, silicates, and clays. Just this is what's called a mineral class map, and it's just a combination of everything that you have all at once. The way in which it's made is the least common mineral will show up first, and the most common mineral will show up last. So that way you just have more texture in your maps. But what you can see really quickly here is that you have a little bit of atacamite in this pink. You have also in pink, you have this gypsum. You have in these purples would be some montmorillonite, so some smectite. Some greens would be this chlorite. So really, the idea though is to understand their distribution for mine planning. So we talked a lot about mineral fingerprints here. So secondary copper minerals, I just selected a few of them here, but these are the spectrum for malachite, for chrysocolla, and for slate. So we know that the principal mineralization is comprised of these secondary copper minerals that include these, a few over here, iron copper sulfates, iron limonites, chrysocolla black oxides. And so this is demonstrating here to us that not only is the gangue mineralogy at Antiquaia complex, so like these chlorites, these montmorillonites, and all these other sulfites, etc., but the ore mineralogy itself is very complicated. And it's also complicated in the sense that it's not just a bunch of different copper-bearing silicates or sulfides. It's all of those plus copper sulfates, copper carbonates, etc. Iron oxides, this is an example. Over here, you'll see this is a goethite. Over here, this is a hematite. So it's about a 350-meter thick column, and some of these will contain some copper in them as well. The oxide zone is what we're mining. So we can easily map these in the veneer because they have these well-defined absorption features. These ones in particular are due to crystal field absorptions, which we talked about. And in addition to mapping just iron oxides in general, we know that hematite is iron 3+ and goethite is iron 2+, and they can be mapped at specific wavelength ranges, which is really exciting. We had a hand raised. Or was it a fake hand? Okay. Hand went down. I was very excited. This is another look at what this hyperspectral imaging data looks like. You can look at it in tabular form. You can look at it just as the iron oxides in just as them separately, or you can look at this entire mineral class map, which can obscure. So looking at this, you might be like, oh, this is all just smectites and gypsum. But really, there's a lot of iron oxide in it as well. So just think of these whenever you see them. Most companies have these summary maps. Just think of them as a summary and then go in and take a look and see what the other mineralogy is actually doing. And like we said, this oxide zone is complicated. This is the class map that I picked out just for this area. So this area, we can see that we have goethite over here, we have hematite over here, and we have this other mixture column here. And this is what the distribution looks like visually. But knowing that in this small section alone, sorry, there's no scale bar, but in this small section alone, you have jarosite, you have these two unnamed sulfates, but they're iron and magnesium sulfates. you have gypsum, you have white mica, you have montmorillonite, you have iron oxide as a general species, chloride and carbonate. And all these, if you think in terms of the metallurgy of it, which we're going to talk about, is going to be very messy. Sulfates, there's a variety of sulfates, which are some are ore bearing, including antlerite, copper, this copper mineral, and oh, this is hard to say, but bronchitite. But then in terms of other sulfates, we also have alunigine, jarosite, gypsum, this general, and these three general sulfates that don't necessarily have a name, but have distinct spectral features about them. And again, you can just see these are what these minerals look like spectrally. And this is where it gets interesting. With sulfate, there's a permeability issue here. So Antiquaria's mine is completely based on mining this oxide resource and then leaching the copper from the oxide and the sulfate ore. However, when there's too much sulfate on the leach pad, things will become problematic. So here we're looking at 500-meter section over here. Here's what it looks like, just looking at it as if you were looking at core. This is just a red, green, blue RGB photo. But then just looking at it from this perspective, you have jarosite, you have this iron sulfate, you have this iron magnesium sulfite, and then you have your gypsum. Now, here's where things become interesting. Talking about the Atacama Desert. The Atacama Desert is the driest desert on Earth. Interestingly, though, the Atacama Desert is also a fog desert. It's a type of desert where fog will supply the majority of the moisture needed by the animals, of which there are animals there, not many, but there are, and also the limited plant life that resides there. The humidity in this foggy air is above 95%. When do you see this fog? From personal experience, you see it in the morning. The average temperature of the Atacama Desert, we can see here. So it's about the average temperatures that you'll see over the course of the year. Importantly, though, it's sufficiently cold at nighttime for the sulfate liquid in the heap leach to crystallize, which then forms an impermeable layer below the leach. So, understanding this sulfate distribution is crucial to this successful mine at Antiquoya. And so then these next few slides, we're going to dedicate towards looking at these different sulfates and appreciating them at the 500 micron scale, and also appreciating how intermixed they are with the rest of the resource. And this over here, as you can see, this is the limit here for the mine. So here again, we can see just how intermingled everything is, and how just generally without the hyperspectral imaging in this case, it would be very difficult to appreciate just how much of these different sulfates over here we have that are not only this crystallizing layer, but then they're also mixed with these 2 to 3 different clay layers, clay minerals as well. Here's another one. This is a little bit lower in the quartz sericite pyrite domain, but it also has sulfate in it. So you can see as well, you have this antlerite and these other 4 sulfates up here that are all intermixed again with the white mica, the keelanite in this quartz sericite pyrite domain. And a little bit of carbonate here in the cyan. One last kind of look at it, just again, really just showing just how intermixed everything is and just how not simple this is going to be for everyone. I want to take a quick look at carbonate. Some of these carbonates here are ore bearing, like the malachite. And to understand its distribution is important because also these carbonates have acid neutralizing potential, which is also problematic for leaching. So they present a problem for heap leaching because strong acids are going to be used to leach the copper from the ore. And at Antiquoya, it's important to maintain a pH of 1.5. But carbonates are natural buffers to acid solutions. So at the micron scale, you have these carbonates that are intermingled with the ore and are also ore bearing. So again, it's not like you can just say, don't mine this block. They're intermingled everywhere. At the 500 micron scale, here's a good example. Carbonates again in cyan, this blue color. But then you have again these sulfates all in these kind of pink colors, and then you have just your white mica and keolinite. I forgot the montmorillonite, that's this purple. And then clay is always a potential complication. So throughout all these images so far, we've seen white mica. This white mica is not yet broken down into muscovite versus illite, but you can do that. Montmorillonite in purple and keolinite in this gray color. At the mine, they estimate that unless there's greater than 10% clays, there shouldn't be an issue in the heap leach or in the mill during crushing, which is another important part of their circuit. But understanding their distribution is important so that proper test work can be conducted. So this gang at Anticoya, this is what it looks like in terms of their spectral fingerprint. And really, the structure of these phyllosilicates in general, how they're formed down to their TOT structures, are important because, for example, at Anticoya, grinding clays can increase mill residence time and clog milling equipment because of their swelling potential. Leaching, clays have the capacity to absorb reagents and thereby can increase acid consumption. So it's just so important to really understand all of this mineralogy. This one I throw in here because, like I said, I'm going to share this presentation with you guys. This is a great summary diagram that I adapted here just to really underline that how much clays matter. And the last one I wanted to throw on here, sulfides aren't really something that are mapped in the veneer where some of them are spectrally active. These are just a bunch of iron sulfides. The iron sulfides are looking more at the veneer, at the visible features over here. But some sulfides, like I want to say galena, they'll have actual spectral signatures. So you're not doing hyperspectral because you necessarily want to map sulfides, but it might be something that is possible. So it's something to ask, but it's not something to expect. All right, unsupervised learning approach to geomet domaining at the Anticoya mine. Over here, we have a picture of Antofagasta, the city. So building a purposeful 3D model. The first thing I did just with numerical modeling, and again, there's no trends in here, but it was just to build more of a highly supervised model that we said, okay, after binning the different minerals into any kind of clay greater than 10%, sulfates greater than X%. After we did that, and then combining them with the chronological order that, okay, the most important thing to map is iron oxides, the second most important thing to map is carbonates, etc. Just to get a kind of feel for distributions, taking this kind of approach, there's nothing wrong with it, but we wanted a little bit more information in terms of if you were to take some test work from this area, what else would you be getting? Would you be getting the same thing as you're getting over here, or would it be completely different? For planning purposes, doing more of a domaining approach, which is what we're going to talk about, is probably the best way to go. So a quick introduction to machine learning. You have supervised learning where your data is labeled. Here you're looking more of classification and regression. And then you have unsupervised learning where your data is unlabeled. Applications here would be dimensionality reduction. So in this case, with us taking, I think there's say 20 some odd minerals, reducing it to a manageable amount of data, and then clustering. So yeah, in this case, we're going to be using unsupervised learning. What I used here was something called a UMAP. It's It's a dimensionality technique, not dissimilar in principle to principal components analysis or a TS&E. The idea really, though, to keep it simple, is to take a lot of variables. So in our case, say 20 different minerals, too many variables for us to all consider at once, and to reduce them to an amount that's more manageable and easier to model in 3D and to cluster. So this was one of the results of a UMAP that was run just on the mineralogy at Anticoya. Here you can see that all the gypsum is plotting in this side, iron oxides are plotting here and here in the UMAP space. Our data inputs. So data inputs are critical for both getting the results that you maybe want, but also there are criteria for using the UMAP. So it must be continuous. So you got to check your drill holes. If you just are picking something that occurs like in one little area, it's not going to be useful for using this style of interpretation. And likewise, the amount must be statistically significant. Unlike principal components analysis, UMAP doesn't like when things are highly correlated. So if your Muscovite and Kilnite, for whatever reason, are inhabiting the same areas, choose one of them. That's just not going to be helpful for the final interpretation. Not including textural variables, which we're going to talk about next. At Anticoya, there's 22 minerals, or for us, we're going to call them dimensions. So textural data. This is probably the coolest thing about using imaging data sets, is that a lot of times people think, oh, they just look pretty. Oh, they're too much information. Oh, what do you do with all this information? The fact of the matter is there's a lot of consultancies out there now that, and universities, there's lots of papers out there as well, where they're actually using this textural data in order to extract parameters from it to use for different applications. So one example here is looking at a GLCM model. And so basically all it's saying is that here's your pixel that you're looking at. How is it related to all the pixels surrounding it? And after the algorithm will cycle through each pixel, it's trying to understand how it's connected. And then you'll get, this is just an example of 4 output variables, but you will get a lot of different output variables that you can then put into either unsupervised texture clustering or supervised texture classification. This is also, this is an example of the gray level co-occurrence matrix, but you can also use this for things like convolutional neural networks. So in our case, we had the 22 dimensions of mineralogy data. We had all this textural information, and then we should see some distinct clusters. So from that, we got from Anticoya 5 different clusters that you can see over here. We can look at the composition of these clusters to try and understand better what they're telling us in terms of geology. Not necessarily, it's not going to be a paragenesis, but it might give us something a little bit to go on. Is this more of a clay domain? Is this more silicate, etc.? Something to note in here is just that clusters 2 in purple and 4 in green are much bigger in terms of quantity than the other clusters. So the other clusters are about, say, 600, and these ones are more 1,600, almost 2,000. So something that you can do is subsequently is you can go and then break out these clusters and then look at them separately. But for the purposes of this investigation, it wasn't necessary. So taking a look at these clusters, cluster 1, I identified kaolinite, iron oxide, gypsum. Cluster 5, chlorite, montmorillonite, carbonate, etc. You're just looking to see just what the average compositions of these clusters are. And in the end, and again, there are no geologic trends applied to this in terms of the model. But in the end, what you can then do is throw these into a geologic modeling program and to then derive meaningful zones for test work selection, because what you can say now is that even though this purple area is here and here and here, they are spatially distinct, but they are mineralogically and texturally similar. So maybe you might not want to be sampling from here and here because maybe the green, a lot of times we're limited by funds, but maybe the green cluster is something that's more important to sample because it has more sulfates in it or something like that. So you can use this now to be much more selective in how you are selecting your test work because you're better characterizing your deposit for mining purposes. Okay, I'm going to show you now an example with regression, but does anybody have a question about what we did over there? Okay. Oh, I like the thumbs up. Thank you. Awesome. Okay, so again, another snapshot of the Atacama Desert is a lot of roads, a lot of, I thought, because I had been to Egypt and there was just lots of sand dunes. I thought the Atacama Desert was going to look like that too. The Atacama Desert is much more mountainous, and that shocked me because I'm from just an island in New York in the United States, not very exciting. I didn't, I'd never seen stuff like this before, so that was very cool to me. Yeah, it's just much more mountainous, and there's just lots of roads just going all through it. So this is very beautiful, but a common thing that you would see. Okay, regression. So we talked about this before. This time we're going to look at something that's more supervised. We're going to use a machine learning model called XGBoost for this one. So what we're doing here is we're going to have our model learn to predict an output from our input data or features. Classification problems require, as we said, features, which are the inputs for prediction, in our case, the mineralogy, and the labels or the classes that you want to predict. In our case, we want to predict their geometallurgical domains, which they call UGMs. So extreme gradient boosting or XGBoost is widely used in both in classification, regression, and ranking tests, including, in our case, hyperspectral, geochem, and geospatial data modeling. And why are we doing this? So the work that went into creating these different UGM domains at the mine was incredibly expensive. And in comparison, even though it looks expensive when you look at, say, oh my God, this is $25 a meter or this $30 a meter, it seems very expensive, but in comparison to all the testing that went into creating these very meaningful domains, it's actually very cheap. So what we want to do is predict this very expensive data set from something that's actually a cheap data set in comparison. So the problem here, so this is called acid consumption. So there's a few different things that you'll see in this little diagram here, but acid consumption, it really can determine whether or not a project is economically and or technically feasible because your copper recovery in this case is going to be directly related to it. So there's a bunch of factors that can play a role in it. You could have the minerals present in the ore, including the gangue. Some minerals will undergo alterations that cause additional precipitate formation. The solution pH is very important, the rate of acid application, as well as particle size. So ores that are going to contain these large quantities of acid often present substantial technical challenges for copper recovery. You have some that are going to dissolve. Some will dissolve rapidly. They'll form precipitates like this. That's going to restrict further leaching. Other acid-consuming materials will gradually transform into secondary minerals during the leaching process itself. And it's possible for these byproducts to restrict further consumption as well as release their own acid, thereby altering this acid balance, which is really, really controlled. So this is the current acid consumption model that they have at the mine. It's based on their alteration types that were defined prior to doing any of the scanning, and also the intensity of the alteration type. So we can see here that the alteration, so to because this legend's hard to see. So you have weak, you have strong, and you have moderate in this orangey color over here. And these are the different zones. So overall, you can see that the alteration zones will consume more acid than any kind of late stage events that are at the mine. But we're going to look at another way that you can use your hyperspectral imaging data using this classification model with the XGBoost. And it's important because when you have these consistent and continuous data sets like hyperspectral imaging, you can actually end up helping to save money over the life of the mine. It is important, however, to say that this is what's currently modeled, this is what's currently known about the mine. If they're going to go start to drill out here, you're going to need more information that's based in all the work that they've done here, because this might represent a new area. And when you start trying to use a regression or a classification model to predict into an unknown area, you will run into trouble. Over here is, so this graph over here, these are the different mine-defined geometallurgical units, or UGMs. So you have 10, 20, 21, etc. And that's what all these different colors are. This line over here differentiates the oxide mainly zone, and this differentiates the sulfates. So these different geomet units ensure that the plan is going to be constantly filled by the correct balance of sulfates to oxides. There's no need to rebuild any of this work. They feel very confident in everything that they've done. But like we said before, an underlying consistent and continuous data set like hyperspectral imaging could allow for the construction of a variety of prediction and classification algorithms. So in this case, we're going to rapidly classify the geomet domains as soon as the core is scanned. And for this, we're going to use an XGBoost. Over here are all the drill cores that were scanned, and this is them labeled as they are just by the work that's already been done by the mine. And then in this, we're just using this correlation matrix just to help select inputs for a classification model, and that's an important step. So wherever we have this data, we can construct our acid-consuming domains. We set this stuff. What we have over here is a variable importance plot, and all this is showing to us is the relative importance of all of our different minerals from the hyperspectral data in predicting our geometallurgical units. So in this case, you can see our top 5 things are the iron magnesium sulfates, the iron sulfates, kaolinite, carbonate, and our RQD pseudo breaks, which is interesting. Here you can see the ultimate confusion matrix and statistics. So basically how well we did. So we have an accuracy overall at this point of about 0.64. Not terrible, not terrible. And you can see too where the model's getting confused. So you can see that, okay, it's actually doing a pretty good job predicting UGM 100. It is getting confused with UGM 300 with 108 times out of the entire data set that we have. Overall, it looks like 300 is getting equally confused by 300 and 400. So maybe it's something that we would have to look into deeper to really improve upon the model before we would press play, kind of thing. The point is that this is something that we can use, and in this sense and in other senses. Questions before we finish up here?
No questions. It's just going more complicated.
We're going to pull it back in. Okay. So why in the end, going back to our title, why did size matter in this case? The first thing is counting statistics. How many signal events like photons or electrons are measured? If you have more counts, you have more confidence in the measurement. You have fewer counts, you have more noise, more uncertainty, and less reliable identification or quantification. You can have improved signal to noise. You can have this continuous spatial coverage. You have greater spectral fidelity, and you have this robust detection of these minor or mixed phases. So all these different sulfates that maybe they didn't know they had before, all these different species of copper, it's endless. The number of pixels, so moving from point to line to scanning data, you can increase the amount of minerals you're likely to see in your projects to help you better understand their proportion in an interval. And when working with hyperspectral imaging, it's possible to see texture. And so with all these advances in machine learning, it's only becoming more powerful for geometallurgical applications. Spatial resolution, we're able to map spectral parameters, complex mixtures, and areas where the core is highly degraded. Most of the core looks like this, very hard to see. We're also able to see that even at 500 microns, there can be up to 6 to 8 minerals in a single pixel, which is insane. Increased spectral resolution will help us see these more complexly mixed minerals. And finally, in terms of spectral resolution, you have better mineral discrimination. There's an incredible amount of minerals that have similar but slightly different absorption features. High spectral resolution will allow us to separate these subtle differences. Detection of diagnostic features. Some minerals will have these narrow, very short, sharp absorption features that low resolution systems may miss or blend these features that could really lead to incorrect interpretations. And finally, you have this quantitative mineral chemistry. So this improved resolution will allow us to track wavelength shifts that are linked to specific cation substitutions, for example, in white micas, that will give insights into fluid chemistry, temperature, and alteration intensity. Here alone, you can see all these different sulfate minerals, of which we saw were so important at Anticoya. So, quiz number 2, the last one. Does anybody have anything that they thought was really interesting that they learned about Anticoya?
Actually, everything that I heard today was new and interesting.
Great. Anybody else? I think for me, the most important thing I found out while doing this entire thing was that, so having lived in Chile for such a long time and experiencing this fog and everything, I had never remotely thought that it would have any geological implications, because it's honestly, if you think of fog, it's normal fog. There's nothing like that looks different about it. And living up in the north of Chile is just like living in any kind of desert. It gets cold at night, and then it warms up quite a lot during the day. And so the fact that just having these temperature differences, having this fog, led to real world mining issues blew my mind. And I thought that was really cool. Yes.
Yeah, so I want to say that was all interesting. I just have one question about Anticoya.
Mm.
So if we talk about hyperspectral data, it can help detect minerals there, right? So the accuracy depends on what the resolution and the type of minerals only.
So I would say two things. If you go into an area where the minerals you're looking for aren't optimized in a hyperspectral system, you won't get a good result. If you're looking at purely if you're going into an area that has a lot of shale, say, and it has a lot of disseminated pyrite, and you want to find out all your disseminated pyrite, and you want to try and map out potentially, maybe let's just leave it at disseminated pyrite. And if that's what you want to really map out, this is not the technology for you, right? So you have to be thinking about what are your questions and what are you trying to map before you do it. Going into a place like Anticoya, they had an oxide zone, iron oxides, which is optimal for anyone that has a veneer system. Not all the providers have a veneer, so it's important to ask. And then also they had a lot of sulfates, a lot of carbonates, a lot of phyllosilicates, a lot of clays that's optimized for the SWIR. They had geometallurgical questions about where are my sulfates, say, where are my clays? What is the base of the oxide zone? All these questions you can answer using hyperspectral technology. So in that sense, we're already in the right ballpark. In terms of choosing your vendor, now that's when you have to be more specific, because do they have a veneer, like we just said? Do they have good resolution after 2300 nanometers? Can they identify mafic minerals if that's important to you? Mafic minerals very well, I would say. Not everybody can. Do you have very complex mixtures? So in that case, what is their spatial resolution? Some people have millimeter sized, some people have 500 microns. And then if mineral chemistry is really important to you, some people have 6 nanometer resolution, some people have 2 nanometer resolution. Asking all these questions, asking for case studies, examples of their work, even if on their website they say that they've worked with a specific project, reaching out to that project, reaching out to that geologist, especially if you know them, all these things become really helpful. Talking at conferences with people, because somebody at some point has worked with somebody. I found working on the vendor side that everybody's always going to complain about something, but it's about listening to what the actual complaints are versus some of the noise that came from it would be helpful. But I find that our community is very open. Our vendors are typically very smart. I don't think not all of them are very hardcore salesy. A lot of them, you'll have very smart people working in them that can talk to you from a technical perspective. And just really asking the questions is going to be so important in the end of helping you. Was that helpful?
Yeah, thank you so much for your answer. I got it. Thank you.
Okay. Anything else that I can help you guys, maybe not confuse you further? Honestly, have a look at the slides. If you have questions about them, send me questions. I think my email's on there. So no worries. Happy to help.
Okay.
All right, Lynn, I want to thank everybody really much for having me, and I hope that you learned something.
Thank you so much. We enjoyed.
I'm glad.
Thank you for the presentation.
Thank you.
You're very welcome.
Goodbye.
So good.
All right. Bye, everyone.